Hi and welcome. I hope everyone is well. In this lesson, we will learn the Poisson distribution. This topic about statistics 2 A level, and I will I start. I'm starting to A level, the first topic. The Poisson distribution related to and according to a binomial or a geometric distribution, but different this distribution. A Poisson distribution can be used to model discrete probability. Please notice that the distribution is discrete probability distribution in which the events occur rarely, singly, at random and independently in a given interval of space or time. In a space, for example, in a square, like time per second, per minute, per hour, etc. The following situation is an example where you count occurrences of an outcome, but the situation does not fit either the binomial or the geometric distribution model. In 1898, Ladislaus Bortkiewicz investigated the number of soldiers in the Prussian army accidentally killed by horse kicks. It was rare for soldiers to be accidentally killed in this way. There was no way to predict when it might happen. Horse kicks happen at random. Bortkiewicz collected the following data over 20 years for 14 army crops. Uh, then we have a table about for a corpse in the kick of the horse kicks happen, and each data point the table represent the number of accidental deaths from horse kicks in one corpse in 1 year. So there are, for example, if we some of the frequency, we have 280 data points in total. From the data, the mean average number of accidental deaths from horse kicks in 1 year is 0.7. So our average, the mean or mean and average, uh, please notice that very little, 0.7 in 100 in 280 events, but our average, our mean is very little, 0.7, and numerous other situations have the same characteristics of rare outcomes occurring singly and random within a fixed interval. For example, the number of eagles nesting in a region, or the number of bubbles in an item or classware, or the number of typing errors per page made by a good typist, a number of an insect type in square meter or all format. All example, please notice that all example according to some particular. For example, all example regards to one singly and independently, and rarely. For example, the number of eagles nesting in a region or bubbles in an item or classware. This situation very rarely, and in a time or in a space. For example, the number of eagles nesting in a region regards to time, or the number of bubbles in an item glassware regards to space, in a square, 1 meter square, for example. And notice that two that the fixed interval can be period or time or space. So if our events interval can be period of time or space, we will think this distribution, probability distribution, regards to Poisson distribution. And for example, the other one, a clinic treats people with severe insect bites. It keeps records for 100 days. On most days, no more than 3 people with severe insect bites attend the clinic. But on one day there are 16 people. It shows us in only one day we have 16 people. These events regards to independently. So the bar chart shows the frequencies. Following the bar charts, we look at these bar chart, and we have 0 people, 25, 25, 26 day, 0 people come in the hospital, and one day, people, each day 1 people. For example, 45 days in come the hospital. But 16 people one day come the hospital. In theory, the maximum number of people attending the clinic is infinite, but large numbers, much bigger than the mean, are not expected. So, to model these situations, you need a different discrete probability distribution from those you have already studied. This type of discrete distribution is a Poisson distribution. And the other one, uh, introduction to the Poisson distribution. First, let us explore Bortkiew's data further. Please remember that we talked about this situation Bortkiewicz investigated. For example, our a table, and the first time, uh, according to this table, we will compute the mean and we will compute the variance. And please remember that if you want to compute a mean, you should use these formulas, and the number of death and frequency, our mean is 0.7. If we want to compute the variance 0.76. Please notice that nu and variance values are very close each other. So the Poisson distribution, mu and variance becomes very close each other. So, and we can see that the mean and variance are quite close in value. When working with experimental data where the outcome or event occurs at random in a given interval, and the mean and variance all are almost the same value. Don't remember that if you work in the Poisson distribution, you should take mean and variance the same. a Poisson distribution is a good choice to model the data further. And now we have a Poisson formula. If the random variable x has a Poisson distribution with parameter only lambda, and lambda greater than 0, and lambda, for example, it means nu. In Poisson distribution, nu means lambda. So nu and lambda the same parameters in Poisson distribution, and also nu and variance the same. So lambda and variance the same value in Poisson distribution. So if you want to compute the x or probability of x, you should use this formula. So the probability of x value and r, or our formula is lambda to r multiply e to minus lambda over r factorial. In this formula, e means Euler number. Euler number approximately 2.71, and in a irrational number like pi. And we should use this formula if we want the probability of x. And we have some example about Poisson distribution. The number of calls to a consumer hotline is modeled by a Poisson distribution with a mean call rate of 6 per minute. In this question, they give us mean, and they tell us this situation about Poisson distribution. So we should think about this problem related to Poisson distribution. And in the call center, we have 6 calls per minute. It means in the Poisson distribution, nu or lambda 6 per minute. 6 per minute. We have 6 calls in a per minute. Calculate the probability that in a given minute there will be 9 calls. And we have a probability of 9 calls in a per minute. We should use Poisson distribution. So x equals 9. We want to compute the 9 probability. So we should use the Poisson distribution. And our formula is x become r. It means lambda and x to x e to minus lambda over r factorial. So this means probability 9 calls, r lambda 6. So 6 to 9 multiply e to minus lambda means 6 over 9 factorial. So it's about approximately when I look at the result, approximately result, this approximately result is 0.000.06 and 88. So in a minute, if we want to take 9 call, this probability value is 0.0688, and the B1, 3 or fewer calls. It means probability of our X value 3 or fewer calls means less or equals than 3. So we should compute the probability of x0 plus probability of x1 plus probability of x2 plus, and the last one, probability of x3. And we should use Poisson distribution, and the R Poisson distribution, if we remember, R probability of R means lambda to R multiply E to minus lambda over R factorial. So, and probability of 0, lambda means 6. So 6 to 0 multiply e to minus 6 over 0 factorial. Please remember that 0 factorial means 1. For example, 3 factorial means 3 multiply 2 multiply 1. For example, 5 factorial means 5 multiply 4 multiply 3 multiply 2 multiply 1. And probability of 1 means 6 to 1 e to minus 6 over 1 factorial. And the probability of 2, 6 over 6 to 2, and e to minus 6 over 2 factorial. And probability of 3, 6 to 3, e to minus 6 and 3 factorial. And this process approximately that, let me please I look at the result, approximately that 0.151. And the other one, they tell us more than one call, more than one call. More than one call in a minute probability, it means probability x greater than 1. It means 2 probability of 2 calls plus probability of 3 calls plus probability of 4 calls and plus infinity. But we should think about this probability is a discrete probability. So all probability sum equals to 1. If we don't compute these probability values, but if we think about all probability, sum of the all probability equals to 1, we should compute the 1 minus 0 probability minus probability of 1. And this situation and this situation the same, or this probability value and this probability value equals each other. And 1 minus probability of 0 means lambda, or it means 6 to 0 multiply e to minus lambda over 0 factorial minus probability of 1 lambda, or 6 to 1 multiply e to minus 6 over 1 factorial. This process approximately that 0.983. Okay, and the last question, at least one call. At least one call means, x greater or equals than 1. It means one probability of 1 call plus probability of 2 calls plus infinity. But this situation, we don't compute this probability. If we think about the all probability, sum of the all probability equals 1, and the different way to compute this probability, 1 minus probability of 0. So 1 minus 6 to 0 multiply e to minus lambda over 0 factorial. So this process approximately that, let me I look at the approximately value that 0.998. Okay, now if you in the question, if we review this question, in the question tell us the situation is Poisson distribution, and they give us the per minute mean. For example, in the minute or square, in a square, you think about the Poisson distribution, and you should use the Poisson distribution formula, this formula. Okay, now the other question about Poisson distribution, a typesetter makes one average 5 errors per page of typing. State the assumptions made to model the average number of errors per page as a Poisson distribution. They tell us a typesetter makes on average 5 errors per page. So it means we have independently and singly and rarely, because only 5 errors per page, rarely events. So it's about Poisson distribution, and we can state the assumptions this situation. In a book with 200 pages, on how many pages would you expect to find at most 2 errors? At most 2 errors mean probability of x less or equals than 2, because they tell us at most 2 errors. So we have in average, it means or lambda or nu, are lambda equals to 5 per page. And in this Poisson distribution means probability of 0 plus probability of 1 and plus probability of 2. And our formula is probability of R means lambda to R multiply e to minus lambda over R factorial and it means that probability of 0 R lambda 5. So, and 5 to 0 multiply e to minus 5 over 0 factorial plus 5 to 1 multiply e to minus 5 and over 1 factorial. 5 to 2 multiply e to minus 5 over 2 factorial. And this process approximately that, let me look at the approximately value, 0.12. So, and they tell us in a book with 200 pages, how many pages would you expect to find? And our expected to find the pages, we should compute that in for telling us 2 in 200 pages, we should 200 multiply 0.12. So it means 24 pages. 24 pages, we can expect the at most 2 errors in a 200 pages. If you want to expect value, you should in the number of pages multiply probability. So in 24 pages, in the at most 2 mistake or errors.